Next up, we have Ary and Max from normal computing. We'll switch from quantum to thermo, and then we'll go back to quantum again. Okay, we have a whole group.
Whole team, yeah.
I'll let you figure that out.
All right. Hey all, my name is Ary Swaminathan, one of our early product GTM leads here at Normal Computing, and I'm joined by Max Aifer, as well as Gavin Crooks, one of the true founders of Thermodynamics, modern thermodynamics, and we also have here our ML lead, Thomas All, one of the former LLM leads at Meta. Many folks, perhaps especially after earlier, might be wondering what thermodynamic computing really is. We're a company that cares tremendously about truth, building, and respecting the opportunity, and we're here to try to cast some sober light and galvanize the community here. So briefly on our founding story, back in 2022, our CEO, Ferris, had dropped out of a physics PhD after less than a day, and he went on to build the probabilistic machine learning effort at Google Brain. He helped spearhead TensorFlow probability and convert probabilistic AI architectures into lighthouse launches and 10-figure impact. Ferris teamed up with his co-founder, Antonio, previously one of the co-founders of TensorFlow Quantum and a Waterloo PhD dropout himself, as well as Matthias, who led strategy and partnerships at Google X across industrials and AI. He was ironically the only one to finish his quantum PhD. So they met helping, to shape the physics and AI effort at Google X, and Normal's mission today is to revise AI foundations to advance reasoning and reliability capabilities in the physical world. This includes, in part, we believe, embedding AI in the physical world itself to help these kinds of architectures and inference scale. This last part will be the focus of today's talk. To be clear, we won't be giving a holistic pitch on Normal, but we will be giving a talk to get the folks in the room up to speed on the progress we've made toward making AI reasoning massively energy efficient. So when we think about where we expect technology to go, it's natural to extrapolate from the past. AI has been getting better and better in terms of its capabilities, but also consuming more and more energy. When you extrapolate exponential growth, trends will only get you so far, right? Because sooner or later, some resource becomes a limitation on progress. And in the case of AI, it's more or less clear that energy will become that limiting factor in the coming years. At the same time, even by consuming vast amounts of energy, we still haven't been able to make AI that can reason the way a human can. Sure, there's been progress, right? For example, by using LLMs to generate proofs that can be checked automatically, we're able to do some of the same tasks that a human does by reasoning. But many scientists, including Jan LeCun, believe we will continue to encounter obstacles when we try scaling LLMs alone to tasks like planning and reasoning. So how do we solve these twin issues of efficiency and reliability? That's the question. But we as a technological civilization have solved these kinds of problems before. So historically, steam engines were the early drivers of the first industrial revolution. Their energy usage became a salient issue, and of course, thermodynamics was developed to optimize their efficiency. And the progress of that theory was subsequently driven by the progress of technology itself. We like to think today's steam engine is the data center. It's big, it's power hungry, and it's critical infrastructure of modern industry. So it's time for a return to applying thermodynamics to our biggest drivers of progress. Similarly, but another thread, exploration and trade historically relied on the predictions of navigators and their tools. So to make the tools of navigation reliable, accounting quantitatively for the unknown became required. Eventually, this was solved by the application of probabilistic reasoning, where methods like the Kalman filter became widespread, culminating in the inclusion of Kalman filtering in, for example, the Apollo guidance computer. So now another parallel, AI decision-making, we believe, is the navigation of the 21st century. Augmenting our AI partners with probabilistic reasoning will bring them the reliability we expect from our most critical tools. So how are we augmenting AI with probabilistic reasoning? Two such paths are upgrading existing architectures throughout with probabilities, for example, ProbML, or pairing generative tools with reliable but expensive simulators or world models. So in the first path, we apply Bayes' rule and probability-aware training to output confidence scores with the model. The goal is to calibrate the model, meaning if it reports 70% confidence, its answer is correct 70% of the time. Reliability then comes from the model knowing what it doesn't know, and low confidence serves as an accurate flag for when the model needs expert human guidance or review. On the other hand, we can bootstrap reliability from a system that we can deeply interpret and understand. Generations from a non-deterministic system, like an LLM, provide fast ideation of potential solutions. They're trained on huge amounts of data, but they act as a black box. So the reliable system then evaluates answers for correctness. In this way, just as Bengio's vision for System 2 AI, we can take advantage of the best of large-scale models and data, as well as interpretable, reliable systems. Examples of this approach include AlphaGo Zero, Alpha Geometry, recent extensions of Monte Carlo tree search to encompass large models. So we know how to make AI more reliable, but how do we make it more efficient? Thermodynamics is the study of the interplay of energy, work, and heat. And we know that as a system evolves in time, energy gets absorbed by its environment as waste heat, requiring us to continually apply work. In other words, all things tend towards equilibrium. So designing and running machines and computers is a constant battle to stay out of equilibrium, which costs energy. But what if we could reverse this equation? What if we instead designed our computers to work best in equilibrium? This is the core idea of thermodynamic computing. Flipping the typical fight against decay on its head to, in fact, allow the system to come to equilibrium and then use that equilibrium to do a computation. So, thus, by working with the laws of thermodynamics instead of against them, we can build computers that use much less energy. And we exploit the mathematical equivalencies between thermodynamics and probabilistic reasoning, and our reliability and efficiency approaches synergize in a way that lets each of them make the best use of the other. As far as the applications that we're tackling first, strategically, we're partnering with enterprises because we believe research progress is best motivated by collaborating with experts on hard problems with real stakes. In particular, our application focuses on semiconductor design and manufacturing. So our work has led to technological feats like the first AI verification of complex memory from product specs and simulations alone. We've partnered with some of the largest F500 semiconductor companies in the world, being some of the most important in the West, and are establishing a closed loop between hardware and AI. This was a topic of a deeper dive, actually, earlier in the week at Reindustrialize Detroit, for any of you who were there. But in the top left, you can see the first application of faster and more reliable design, debugging, and verification. This focused application of probabilistic reasoning allows us to directly chip away at the bottlenecks in the trajectory of Moore's law from the inside. In the bottom right, you see our first PCB prototype. That's emblematic of our co-design of hardware and making probabilistic reasoning even more efficient in the process. So just as probabilistic reasoning and thermodynamics have synergy in the abstract, our first products and applications in semiconductors synergize. On the software side, we uncover the computational and efficiency bottlenecks specific to semiconductors, allowing us to more directly target our novel hardware co-design efforts towards useful and valuable problems. And then we take our learning from co-design and apply them back to the product, which allows accelerating the pace and quality of our offerings in loop. As this positive feedback loop converges in the future, we envision like an Ouroboros-like convergence, right, of self-assembling AI that can in fact program and manufacture itself. Heady stuff. But eventually, the convergence of hardware for AI and AI for hardware will in fact enable us to reach the limits of reliability and efficiency as allowed by the laws of physics. So as a first note in that direction, right, we're working across the value chain within semiconductors. We're transforming automation across the whole fab. This is difficult problems across, the whole fab. So we're triaging equipment failure, and then we can tie that, for example, to defects in chips. And we also, wholeheartedly believe that eventually we can transform the entire vertical motion that goes into self-assembling AI that can program and manufacture itself. From an economic perspective, this means we're dealing with some foundational issues in our industries already today that are plaguing our critical infrastructure, right? Among them, talent shortages, geopolitical, existential risk. And you can see some statistics here that certainly paint a powerful picture. But in summary, we're already introducing tech at Normal to address some of these problems. What we anticipate is that scaling it out to more industries at lower cost is possible with the benefit of thermodynamic chips. So enough at a high level. I'm going to hand the mic over to Max, who's going to take you through some details.
All right, thanks, Ary. So we've seen some of the guiding ideas behind thermocomputing and a bit about the impact it can have. And now we're going to start to get into the specifics of how do these devices actually work and how do they differ from other computing devices. So as I'm sure many of you are aware, in a digital computer, information is represented as zeros and ones, or as high voltages and low voltages. And a lot of energy is actually spent on making sure that the voltages stay at those extreme ends of the range to make it easy to distinguish 0 from a 1. Or in other words, a lot of energy is spent in making sure the device stays out of equilibrium. Now, what's different about a thermocomputing device is that it's actually designed to operate in thermal equilibrium, where fluctuations are the rule rather than the exception. And by harnessing these fluctuations, we can sample from probability distributions of interest very efficiently. Okay. Now, it's only useful to sample from these distributions if the distributions themselves are actually relevant to some problem that's important, right? So how do we figure out what distributions we want to sample from, and then how do we actually embed them in the thermocomputing device? Well, so we start with a model of probabilistic reasoning, represented here as a last layer uncertainty quantification method like SNGP. And then we take the target distribution that we want to sample from, and to transfer it to the thermo device, we deform the potential energy bowl of the system such that its shape corresponds to the target distribution that we want to sample from. And then to draw samples, we just measure the state of the system, and these are the samples from the target distribution we're interested in. So that is the general theory of thermocomputing. But how does it actually work in practice? So as an example, let's look under the hood of the first thermocomputing device that we've built at Normal, right? So the most common probability distribution in all of physics, statistics, and many other fields is the normal distribution. And actually our company is named after the normal distribution. Now, these are the simplest distributions to work with mathematically, and they turn out to be very good models of all kinds of different random phenomena. So the first device that we've built at Normal is capable of sampling from 8-dimensional normal distributions. Now, there's plenty of problems that this device can't solve, both because it's so small and because it's limited to normal distributions or Gaussians. But it's still a meaningful proof of concept of the key ideas of thermocomputing. So the basic building block of this device is something you would have seen in any undergrad physics curriculum, which is a damped harmonic oscillator. And you can think of this as just a mass attached to a spring, which is damped by some drag force. And this is actually analogous to an electronic system, which is an RC circuit or an RLC circuit, depending on the amount of damping. And so we can implement it electronically as that circuit. And now we can add a layer of complexity by taking a number of these masses and coupling them together by a network of springs. And this is now analogous to a collection of RC or RLC oscillators that are coupled together electronically. So now you have to imagine that this system is in a thermal environment, and so it's under the influence of noise. And that causes the voltages to fluctuate. And so when we measure the voltages at an instant in time, we're drawing a sample from a distribution, which is a multivariate normal distribution. And it turns out that the mean of that distribution is the solution to a linear system of equations, and the covariance matrix of that distribution is the inverse of a matrix, the coupling matrix that tunes the couplings between the oscillators. So this first thermodynamic computer we've built can only solve problems in up to 8 dimensions, and it doesn't compete with the GPU at this stage. So you may wonder, why do we think that devices with this architecture will actually matter? Well, one reason is that we've proven theoretically that problems in linear algebra, like solving a linear system or inverting a matrix, can be solved with a lower computational complexity using a thermocomputer than using state-of-the-art digital methods. And that means that if we can build a large enough thermocomputer, then the thermocomputer will win over the GPU. Of course, asymptotic complexity advantages don't always translate to real-world practical advantages. Because while it's true that order of n will always beat order of n squared for a large enough n, that n could end up being very large depending on the coefficients. So we've done a number of numerical simulations for different problems, and we found that problem sizes on the order of 1,000, we can get a practical advantage with a thermo computing device. And we didn't stop there, and we've actually built experimentally a thermo computing device that, as I mentioned, could sample these 8-dimensional normal distributions, and we were able to use it to invert a matrix, this matrix here, and that's the inverse that we were trying to get. And you can see as time goes on, we gather more samples and we get a more and more accurate estimate of the inverse, ultimately getting around 26% error. Okay. So now I want you to think back to that picture of the Ouroboros that Ary mentioned, the snake eating its own tail, right? So we've talked about the head, which was this new hardware substrate for probabilistic AI that's based on thermodynamics, right? And the tail, which is the incredibly complex and high stakes design processes of the semiconductor industry. So how do we actually get to this point of convergence where AI is starting to design its own hardware, right? So the first step is to build a thermo computing device in silicon, which is what we have planned for the next year. And our first chip is going to be capable of Gaussian sampling and linear algebra problems up to 256 variables and achieving around 95% accuracy. So this is basically going to be a testing ground for solving the problems we need to scale up to even more useful sizes, basically. So from there, we're going to increase the size and accuracy of our silicon design to get to 1,000 dimensions, meaning we'll be able to run Bayesian inference workloads on the device for small AI models. And this is where we're going to start to see the first signs of thermo hardware supporting reasoning tasks to address some of the simpler parts of hardware design. But to actually attack the problems that are actually relevant to industrial processes, we'll need to scale even further, at least to the order of 10,000 dimensions. And this stage is, of course, more speculative because what that hardware will actually look like depends a lot on how we solve the challenges along the way. And a number of details aren't fully worked out, such as whether and how we will incorporate nonlinearities into the device, for example. But things start to get very interesting at this point because we begin to see the Ouroboros eating its own tail. We'll be able to run probabilistic ML models on a chip where probability distributions are first-class citizens rather than unfamiliar visitors. And these models are going to help us reason about how to build the hardware that isn't even on our roadmap yet. So in other words, we'll know we've succeeded when AI can understand and improve its own hardware fully in the loop with human experts, and our devices are going to be built by AI and for AI. So thanks, I'll hand it back over to Ary.
Sure. Thanks, Max. Yeah, I guess winding down here from the core talk, I just want to switch tone to one brief call. You can, increment it. Yeah, just want to switch tone, right? One brief call to action. I want to let everyone know that we are hiring as part of our incredible and ethical team. We've raised over $45 million in dilutive and non-dilutive funding, and we count as customers and partners multiple Fortune 100 semiconductor and industrial companies. So, you can see Yu Chen, our head of product, former head of product at Google Brain spinoff Clarif AI, Zach, our silicon lead, former CTO of Radical Semiconductor, and Patrick, of course, former head of quantum at Los Alamos National Lab. We were founded in 2022 as the first thermo computing company, and subsequently have released all of the foundational literature in the field. Last note here, I view some of what we're discussing today as bigger than technology. With deep tech, we have a huge ethical responsibility to come correct and build correctly, meaning that companies like ours have been entrusted by our investors and other supporters to make the most of our opportunity to revolutionize computing. As you can see, concepts that go well beyond computing as well. So as part of this commitment to truth, we like to open source our work and publish along the way. Please stay tuned for more, and do check out the QR codes here if you wish for some of our recent works. Thank you, everyone.